that the nature has different scales from outer space, cosmos, to atom and elementary particles. Today, we will consider one part of this scale, nanoscale. Do you understand what I'm talking?
Yes.
Do you? Do you read? Can you see all the letters here? Because I will show tiny nanoparticles. Do you? If you do not, please sit closer so as to hear.
To that.
So, the terms of nanoparticles and nanostructure is limited with the scale from 1 to 100 nanometers. And the volume is from 1,000 to million atoms. So tiny particles. So that's why the physics and chemistry of nanoparticles completely different from even micro, let alone millimeter or nanometer, big stones, and people like us of meter scale. So some part will be written in Russian because I took it from Russian textbook for students. I like them because they are very clear, but others are taken from English-speaking books, Indian, others. So you will see two parts. So, nano, it's a Greek word, means dwarf. In English, in Russian, karlik, small. Then, a bigger one, there was Faraday who introduced the term zone of arum. Tiny particles, even closer than nano, but bigger than one atom. You see, it's intermediate. Then, bigger colloid. It was, this term was introduced by chemists who tried to extract metals from solutions. So the first particles were colloid. Then they grew to bigger particles and big metal pieces. Then in air and in water or other solution, there are also tiny particles which are called zo or gel. Only in 21st century, it was introduced the term nanoparticles. But you understand they existed long before, from Greece and at least in nature. This is a classification of geometrical dimensions. It is not real, it's just a schematic. Such a cubic almost do not exist in the nature, except salt, sodium chloride, you know, sodium water. It's a cubic. Many of other materials do not make cubic. They can be hexagonal, rods, rhomb, and other shapes. So it is the simplest. So they can, the small particles, they call it clusters, nanoparticles, colloids, and quantum dots. Maybe you heard it from semiconductor course. Quantum dots. It's all synonyms, the same. Just they took different terminology. Then, if it's elongated, nanotubes, fibers, rods, you can see it in nature, of course. Then, films and layers, layered. Maybe you know graphite, you can write with pencil because it's layered. Tiny layered, they removed from the rod, and you can read. Then mica is sparkling particles on the sand. You could see and all alloys metals, which are actually polycrystals. So, and there are also some nanoparticles, like a fractal clusters or threads. It looks like a tree. It looks like a coral in the sea, but in the bigger scale. But they begin from this nano size and reproduce the shape. Tiny nanoscale, this and bigger. You can know snow particles of the same structure. When on the glass, the ice grows like fractal. It's a property of water molecule, which prefers to make these fractals instead of being just a cubic or row. So, what is the secret about the nanoscale physical and chemical properties? The whole secret is on the surface, which is curved, very, very developed, and almost all particles, all these thousands or even billion atoms are distributed on the surface, and nothing inside. So this is surface, very, very chemically and physically active. That's why they have a particular properties on this slide. And many secrets of our nature could be explained with this nanoscience. Because macroscopic pictures, they could not explain this giant intensity of luminescence, this very active chemistry and catalyst you may be heard from chemists about catalysts which enhance the chemical reactions. So two ways in the nature realize production of nanoparticles, top and bottom. In even Russian textbook and English-speaking textbook, they show very, very simple cubics, like a movie multi-film for children. But maybe it's real, more real. So, from bigger particles by mechanical drilling, you can make very, very tiny samples. This approach means top. It takes mechanical energy, which is spent on increasing the surface, actually. Because here the surface is comparable with the volume. And the more tiny, the smaller particles, the more contribution from surface atoms comparing to bulk. Do you understand me? Do you follow? So, what is the nature? Let's say beach of the ocean or the sea or the river. Water. It washes and makes stones to transfer to sand. Then from sand to dust. Then Zogel, which can be driven by air and fluid in air, and we can smell it and digest. The other way is electric discharge, lightning, atmospheric. If it hits the electric conducting stone, for example, iron stone, it will discharge and mechanically split the bigger surface. explode lava, thermal and plasma energy also spent on drilling, on the milling of bigger particles to small particles. And they can even evaporate it from this. And you can see the clouds of dust, of ash, at the lava, and so forth. Examples from natural nanostructures. The most simple way is a silicon oxide glass. Glass is not so dense as the salt, sodium. Each atom, sodium, chlorine, very, very close packed structure. But in silicon oxide glass, it is cell-like. Each cell has the size from half nanometer to a few nanometers. So even molecules and clusters of iron or gold or silver can be soaked and stacked inside the glass. This is a quartz when all is crystalline. It's amorphous, it's crystalline. The same cells, but of the same form, shape. Now these are stones which people found on the beach or after cooling lava from volcanoes. And usually as soon as volcano slips again, people climb up and find these gemstones. Some of them precious. Maybe this part is interesting for girls. But others are just glass which trapped gold. Ruby stars, you know, in Moscow, on Kremlin. It is not ruby itself. It's aluminum oxide with chromium, with gemstones, very precious. But the color is completely the same because it's nanoparticle of gold in glass because they can make them very big. So this may be spinel or ruby, and it also can be just glass with our own nanoparticles. And only chemists or physicists can tell the difference if it's a precious gemstone or it's just a bijouterie, as we say. Bijouterie is cheap stones on alloy, even not on the silver. Here you can see how gold can stack over the glass on the surface. This is a reference sample. When we adjust scanning electron microscope, we should adjust the device. Once we can see these particles on the glass, the microscope is okay, is tuned. Here, this again microscope is all taken this at the center of advanced technology, where we started researches from 1960 for 2016. This is a graphite. Once you focus electron beam, it charges, and tiny layer of one-dimensional or two-dimensional film begin curling over, because maybe it's energy efficient. So in this way, it's semi-transparent even for electron, because it's just one thing. Electron can just penetrate through this cage. That's why it can disappear. So it's a very perfect. This is a classic in the United States, and in our country we also put it as a tube with a carbon, just black coil, open. Then electric discharge And there, after a while, on the inner wells of this tube, you can see this fluffy structure. Then you take the scotch, just put it, remove from the tube, and put on the microscope. What you can see? These sparkling particles are iron, on which these fullerene or carbon nanotubes are grown. Their cross-section or diameter is about 1 nanometer, more or less. But the length can be even this big. But anyway, nevertheless, it is one-dimensional nanostructure. So I show you all the examples. Now, why do you need to know this? Maybe it's just a curious fantasy or business of scientists who take money from the government and enjoy themselves watching these nanoparticles. I show you which enterprises in Uzbekistan actually deal with nanoparticles. Let's start. Water purification. You can, of course, as your grandfathers and procedures, just pour sand or pour ash from cotton, and dirty water can be penetrate through these filters and become clean, so as you could drink it. But you cannot kill microbes. You can make it transparent, but it is still not drinkable. But if you do it with nanoparticles, they somehow stuck all microbes because of electric charge on the surface of these nanoparticles. Microparticles cannot do it. So the better filters for purification of water are nano-sized nanoparticles. And in Uzbekistan, there is our secondary enterprise, Green Tech, which one of our colleagues, Haidarov Renat, he produces a small set of devices for purification of water. Not cleaning, purification. It's stronger than just cleaning and making it transparent. It's really drinkable, and they produce it for hospitals, for children, especially. They started from Karakalpakia, because there was the worst water. Then in Kashkadarya, also not good water. In Bukhara, salted water. Who live there, they know the water is not good. But this system can purify it. Then, turbine, hot heating. All the systems related to water need cleaning or purification. Our country buys all this for current. We sell gold, gas, and buy this, which we could do ourselves. So it's your job in the future to do it. Then, system of air purification, almost the same. I didn't have time to translate all from Russian to English. I was told it just 2 hours ago. So, system for natural gas purification. You know it's always smell because the sulfur is added there, or nitrogen. It should be removed from there, but if there is not any, how to say, detectors or indicators, you cannot understand if your gas is leaking or it is closed. Right? So, but it should be cleaned from this. Then, again, nanocatalyst. Our chemical from oil production, they need in catalyst to quick oil. Oil to gasoline, to petrol and other fraction, and also to black oil, which is also used for heating of thermal electric power stations. And the catalysts are imported from Japan. And Japan make the catalyst, or they say that they make them from platinum so as to take more money, but actually it's nickel nanocatalysts, which are plenty in our plants, in Almalik, in Chirchik, and others. But not knowing, we bought. So now is the process how to replace Japanese catalyst with ours. So it was studied. Wait, sir? Then, very interesting, nanogrease is for automobile engine. You know there are 4 pistons. The pistons should be greased to remove friction. But if you add copper nanoparticles, you can not only grease but also polish the piston and the valves. So it is produced by Moscow Engineering Institute, but in Uzbekistan, this technology is already taken, but not. Then medical, you know, all these masks and other devices, they need this. And also cosmetic. Our girls, you know, sometimes you can see this box filled with micellar water. It's just water. Then our room water, yes, nanoparticles of gold. I don't know, maybe they sterilize the face, but they cost much more. What we need, not yet produced, fuel elements for green energy is a hydrogen fuels, thermal electric stations, and fuel for atom electric stations. Supercapacitors. If you want to sit and drive electric car, the main part is capacitors and super batteries instead of tank of petrol. Nanofilters to clean. It is for air cleaning. And nanostructural solar elements, which are expected to have a higher efficiency than crystal silicon. So, now it's deeper physics. Those were just multics and economic speaking. So, if I convinced you to study this deeper, because it's a many working place for you in your life and your career. What happens? You know, nanoparticles of gold is metal. Metal has free electrons. In nanoparticles, these electrons are so free, not so free as in bigger metal, because they form Fermi gas of independent electron, which have plenty room to float over the Fermi level. But on nanoparticles, there is no room for this electron to be independent each from other. So they feel the electromagnetic field as collective. So they correlate each to other because they have only 1,000 or billion. So these small particles, when optic, you know. 400 nanometers violet and 900 nanometers is a red. So it is 10 times or even 20 times more than the size of one particle. So this particle experiences the growing electric vector. And this particle already negative, the opposite. So they polarize. So electrons are here on the surface, and the positive, the rest charge. So are collected on the other part of this particle. So it is dipole. And dipole, when this propagates the light, they become oscillate in opposite way. So this response is very intensive, not individual transition of one electron from this level to a higher level, as we used to hear from optics or from semiconductor, when from lower orbit to higher orbit. This is collective on this size and limited this surface. But they are correlated by optical wave, 400 nanometers. So it's particularly different situation than you heard in the classic optic. It's nano-optic. Then, what happens, how to calculate? They calculate that there is the transverse, normal to the light propagation, and longitudinal oscillation of this plasmon. Therefore, such a system will have one optical band and another optical band. And before, scientists thought that it's just electron transition from both from the basic level to the upper level. They took, they removed, forgot about heavy particles of gold and came to the lightest metal, lithium, you know, in the table of Mendeleev table. And the strongest lattice, lithium fluoride, is the famous X-ray detector in all medical equipment around your university. Medical equipment, it uses this material, lithium fluoride. What happens in this plain lattice, crystal lattice, when it is irradiated with even X-ray? Fluorine is gas. Once it takes energy, the chemical bond between lithium and fluorine is broken, and fluorine goes out. What's lithium? The less lithium. And lithium begins collecting into tiny particles on the surface. You know, it is the lightest atom with the minimal atom size. So the electronic density of lithium metal is the highest in the all chemical elements. That is what you know, that your solar cell phone has lithium ion battery because it's the highest density of electrons. So there was a Ukrainian, he's still alive, and he lives in Donetsk, Radchenko. He calculated and found that if the particle of lithium is 1.5 nanometers, it absorbs the light like this. If it's bigger, the intensity is higher and the wavelength shifts. Here is another part, from 12 to 800. from maximum to a minimum. It is calculated for spherical particles, but it's not the case. Nobody knows what is the shape. Then he suggested, what if the lithium is collected as a rod, nanorod? What will happen? He calculated there appear two maxima, transverse and longitudinal plasmons. Two plasmons because of different shape. If you have sphere, there is only one plasmon, only one wavelength band. The bigger particle, the longer wavelength of this plasmon. Very clear theory, and explains everything. Again, to aurum and argentum, each metal has its own wavelength. So optics can distinguish which metal is in nanoscale form. Optical techniques. So those who study at the optical chair, you can find your work as for detecting. And again, another example, how the spectra depends on the size. The bigger size, the broader absorption. Again, come back to our gold, because the problem of detecting and extracting of nanoaurum from our waste in Al-Malik, Navai, Zarashan has not been resolved yet. The technology which is used now can extract only 2 grams per ton of gold from the ore, digged from underground. But people understand that there is still gold, but tiny. But how to extract it, they do not know. And no, yet there is no technology which would be considered as economical reliable. So there is, in principle, you can extract everything, but you will have to pour their акварелия, царская водка, да, которая растворяет все. Акварелия. But it is very expensive. You can see this solution of gold, depending, the color depends on the size. The same as in bijouterie stones, which I told at the beginning of. This is a different absorption spectra depending on how the particles stick each other. Single, pair, triplet, longer. You can see the same optical bands if it's single or there are 4 as a quasi-sphere. So the problem again, how to distinguish them? Quantum dots, if you heard it from semiconductor lecturers when you studied the course of semiconductivity, you maybe know this. So, do you know about zone theory, band theory, ground state of electron system, and excited state of the electron system? So, if atom, you can see the ground state and the excited state. And when you absorb, the electron jumps here, then 10 to minus 15 seconds, it goes back. But if it can make luminescence, other emission, the electron will have to stay longer to find this probability. It depends on probability to come back. And absorption, no probability. Absorb, remove. Observe, remove. Very fast process. If clusters, the forbidden law will make them to distribute over different layers. And the same is for excited states. When nanoparticles, more options for electronic state and more options for excited states. And what happens? This is macro. Valent and conductivity is penny level, metal. In semiconductor, it will go here. In dielectric, nothing here. No. So. And these are solutions of semiconducting cadmium telluride nanoparticles, which make very, very bright luminescence depending on their sizes. You can see from red to green, depending on size. And this is the equation which shows the dependence of this gap on the radius of nanoparticles. It can vary as you like. From one material, you can make light-emitting diodes any color as you want. This is again photo-induced electron transfer. It's what I said. For free receptor, and if there is irradiation, luminescence, it will go back to the bound reception state. I would want to, before we talk about electric vector of electromagnetic wave, but there is also magnetic vector of electromagnetic wave. How can we use it for determining nanoparticles? You can see this electron spin resonance. There is such very, very powerful technique. You can see how it depends on the irradiation dose, and actually it depends on the size of particles, because the higher dose, the larger particles can be produced. And you can follow the shape of this signal. And again, if you come back to sodium has big paramagnetic resonance, super paramagnetic resonance, which may be one of the reasons why now lithium battery are going to be replaced by sodium battery, because lithium doesn't have such a property. But sodium, it is cheaper, it's available, plenty, even zero, and has also magnetic potential, let's say, on the surface, besides electric. So both as electron, it's more has more capacity than lithium. So now there is a tendency to replace lithium batteries with sodium. But each of them has their own good sides. Maybe they will exist both. Here I would want to show what nanopowder of nickel as a magnetic catalyst, not only chemist. This work now currently is going to proceed with Al-Malik mining plant in Uzbekistan. You can see each nickel is a small rod, both magnetic and electric dipole. And magnetic, tiny, tiny magnetic. So its efficiency much better than platinum. Platinum is not magnetic. And nickel is magnetic, nuclear magnetic. And it's considered. So this is very good picture, which is the basic for collaboration with our mining plants. Now, again, we'll come back to gold, because plenty books, papers are devoted to gold everywhere. Japanese, they do not have dry deposition. They take gold, platinum, and also from the ocean, from solution, from salty water. And what happened? Again, electron beam technology. It's a device, radiation technology. So imagine the substrate. You put here the gold solution, golden gel. Then this is spin collecting, homogeneously. Then if you put there electron beam and want to write gold, those places where the electron beam hit, there is chemical radiation, chemical reaction, and organic is evaporated, and gold is staying there. Gold is difficult to evaporate with the electron beam. Too little mass, too little capacity. You can see this in electron microscope. You can see what was first, then increasing. This was removed, and then there is a chemical process, pyrolysis. This is this thermal radiation technique of drying. And you can make ordered golden spots on the surface. It's a device. And if you do nothing, just electron radiation, there will be fractal picture, not homogeneous. In sodium, again, for portable sodium batteries, you need make electrode. The electrode should be cheap, but the surface should be activated with sodium nanoparticles. Then it will be very, very important. This is non-irradiated surface. You can see layers of atom, then atom. The height of this step on the surface is 3 atom layers, just 3 nanometers. Then we begin to irradiate with electron beam. This electron beam exists in our Institute of Nuclear Physics. So what happens? Where electron beam, the electron hit, chlorine evaporates, and sodium collects on the here. So it's depending on the dose. And the temperature was found, which is S stresses. This one more very tiny microscope, atom force microscope, maybe you heard about it. Okay. If you cut the sample, there will be nano dot and nano well. And the tip of this device has electric potential, and it moves, and by electric repulsion, it jumps up, jumps down, and reproduces the surface of this material. The resolution is nanometers. No one electron microscope can do it. This is next generation of the picture looks like this. You can see these microns, and the height, the brightest, the highest, just below 1 nanometer, 0.8 nanometers, this one. And this is here, background. These are steps of atom layers. So you can see. And after irradiation, brighter, so there were only 0.1, below 1 nanometer. And here, they already 25 nanometers, like rods on the surface. And this is very active electrode, because the surface, all the surface can accept electrons, unlike this small surface is smaller, much smaller. So the task for electrodes, supercapacitor, to make very, very high surface on the area, small area. Only in this way you can make this surface clear. So why people are interested in sodium chloride? Because it's a matrix for nuclear waste. Because if atom station work, the waste should be taken somewhere. The best place is sodium chloride, but not in the ocean, but better in the rocks, in mountains. Somewhere deeper, maybe worked out well, where all gold was taken and the well left. Good. How much time do you have?
About 20 minutes.
20?
Yes.
Ooh. So, one more experimental technique, X-ray deflection. The mechanism is not just plain when the electron hit, scattered, and the picture of scattered electron make the image, In X-ray, the X-ray, depending on angle, they take the reflected X quanta from each atom place and make reflection at particular angle. Here, here, here. So if you rotate angle, you can see chlorine. Right? Chlorine, different layers of chlorine can be seen. Sodium also can be seen. Tiny peaks over the big sample of sodium, which has very strong reflections. But the modern device has a logarithmic scale here, not linear. So if you make logarithmic scale, you can see both the big one and the tiny one. This maybe you collect 1 million gamma X-ray quanta from one layer. And here is just 200, 2000. So the difference is huge. And logarithmic scale allows you on the modern device to see both and analyze this system. So this, and this is the example of copper polishing crystals for combustion engine. You can see what happens. At first, it's just copper, and after working and interaction with the wells of crystal, there appear oxygen. It takes oxygen from the pistol, and in this way it polishes the surface. But the pistols made of brass, copper alloy. Only in the expensive cars like Mercedes, I don't know, whatever, next year they do not have copper crystals. So you should find other polishing system, maybe based on aluminum or iron. This for expensive cars. Therefore, our after service were very curious to take this powder. Then, the last major application of nanostructure for obtaining hydrogen fuel from water. It's the cleanest way of taking energy everywhere. Because water you can find everywhere. Even in the desert, in Karakum, you dig deeper, you will find water. So, it is the real nanostructure. You can see here, silicon crystal. Always, the silicon crystal is covered with amorphous silicon oxide because it oxidizes, amorphous. Then, this layer, very hydrophilic, little bit water, for water. But the water, the nanometer layer of water over silicon is not the real water. If you cool, it will be just intermediate, like a grazing, sliding layer over the ice if you freeze on this system. And then electric discharge. And water will be split here. And if you make the bias, plus, minus, hydrogen will move to negative, and oxygen will be collected on positive. You can get hydrogen and oxygen. And if you fill your tank with water, and two fluxes of hydrogen and oxygen will come to your energy to engine, and when they recombine, the energy, heating energy appears, and the vapor will rotate the turbine, and it will be turbine engine of hydromobile. But it's not so good. People try to make electric engine, which has a higher efficiency. So this is on the way of design, and made on, if we use radiation as a byproduct of atom station. The atom station can produce not only energy from nuclear reaction, but also as a side product hydrogen and oxygen for medicine, oxygen for breathing, important, so important before, but now it is. So it is a byproduct of atom power station. In Russian, it is in Russia it is realized in all atom power stations because they want to transform to hydroelectric engine, small, away in mountain, in resort area, away from power stations. So this is another explanation of what happens from different textbooks. Maybe I'm coming to a finishing because we should leave some time for questioning. So, what I used? I liked, my native language, Russian. I was born in Russia. I studied in Russia. So, but I studied English because I realized that maybe 5% in Russian and 95% in English. All China, Japan, Korean, India, they speak in India and China, but they do science and technique in English. And all books written there are in English. And this is Russian, very good. With semiconductor, Nobel Prize scientists. I like this books. And, this is from the London College. Many pictures, like a movie, very plain, are there, but there are also mathematics. Maybe I'm finished.
Sağ var mı?
understood something. If no question, that means that I was too perfect, which I do not believe, or you were not attentive, or I was told by our professor that there are 5 types of students. One is transparent. The information comes to one ear and goes out 100% without interaction with the brain. And the best, the opposite kind, it makes only 10% by the estimation of London College. They said that only 10% they get the information, they transform it, and nothing goes out. But the head becomes bigger. I hope your head will become bigger.
E.M.Ibragimova, sizga kattakon rahmat. Hurmatli talabalar, ana sizlar nimaga 3-chi kurslarimiz nanofizika asoslarini o'qidinglar 5-semestrda. 6-semestringizda nima bor? Nanomateriallar fizikasi bor. Marhamat, E.M.Ibragimovni hozir nanozarrachalar va nanostrukturalarni tadqiq qilishni metodlari, eksperimental metodlari haqida gapirib berdilar. Men o'ylaymanki, sizni nanofizika asoslari faningizda va nanomateriallar fizikasi asoslari fanida bu mavzuga tegishli dasturda kiritilgan mavzular bo'lishi kerak. Marhamat, kimda savollar bor? Aynan nanozarrachalarni tadqiq qilish, nanostrukturalarni tadqiq qilishni eksperimental metodlar to'g'risida. Juda yaxshi ma'ruza bo'ldi. Mavzuman chala bilaman, ingliz tilini, lekin tushundim. Mana bu prezentatsiyada ko'rsatilgan materiallarda nima haqida gap ketayotganligini, E.M.Ibragimovni nima haqida gapirayotganligini men tushundim. Bu degani juda sodda tilda tushuntirildi bugungi ma'ruzamiz. Kimda nima savollar bor? Bugungi ma'ruzamiz yuzasidan savollaringiz bormi?
Where are you going to work? My question to you. Did you think about it? Where to work? And how to apply your knowledge? I show you open places. Plenty places.
Bugungi ma'ruzamizdan xulosa chiqargan bo'lsangiz, qanaqa takliflaringiz bor? Sababi men bugun birinchi bo'lib E.M.Ibragimovni boshlab berdilar. Yadro fizikasi institutidan kelib. Qolgan ma'ruzachilar qanday ma'ruza olib borsa sizga qulayroq bo'ladi. Yadro fizikasi institutining ilmiy kotibi ham o'tiribdilar. Balki bu kishi keyingi keladigan ma'ruzachilarimizga sizni taklifingizni, sizni beradigan mulohazalaringizni yetkazib, shu bo'yicha tayyorlab kelishni yetkazadi. Qanaqa takliflaringiz bor? Keyingi ma'ruzalarimiz qanaqa shaklda bo'lsa sizga tushunarliroq bo'ladi?
Biz bilamizki o'sha Afg'onistonda juda katta litiy zaxirasi bor, to'g'rimi? Uni ishlatish mumkin, o'sha hozirgi yarim o'tkazilish tanqisligi davrida ishlatish mumkin. Shu bo'yicha Amerika yoki Xitoy proyekt bo'lyaptimi o'sha zaxiralarni foydalanish bo'yicha?
Я поняла. Литиевые месторождения в Афганистане.
Is there any project to use these resources in China or in the US?
I think it not only is, but it was, because it was one of the reasons to get there and stay there. And people were busy with marijuana and other narcotics. And simultaneously, some people were paid by United States experts and dig out precious stones, I know, emeralds это изумруды, зеленые камни, любимые мусульманские камни, да? Emeralds were digged out. Spinel were digged out. Diamond also were found and taken. So a lot of natural precious resources were taken without any contract with Afghanistan.
Keyingi savol.
Hurmatli talabalar, bosh savolga ishora qilmoqchiman. Birinchidan Afg'onistondagi o'sha litsey konlari hali zaxirada. Ular ochilgani yo'q. Ochilgan, topilgan, shunaqa katta zaxiralari borligi, lekin ular hali qazib olish, boshqa ishlar bajarilmagan. Bilasizlar, Afg'onistonda qanaqa holat, o'shaning uchun bu yoqqa hamma kirib borishdan qo'rqadi. Albatta, Amerika, Xitoy hamma shu joyni zaxiralarini egallashga harakat qiladi. Shuning uchun ham balki Afg'onistonga yordam berib, Xitoy boshqalarni qilayotgandir ham. Lekin bu hali bo'ladimi, yo'qmi, hali noma'lum birinchidan. Ikkinchidan, litsiyni kelajagiga unaqa ko'p qolmadi. Umuman olganda litsey batareykalari sifatida. Chunki uni o'rni yaqinda kremniy va uglerod nanozarrachalari, fluorinspar trubkalar va hokazolar egallaydi. Hozir bu dunyoda juda ham katta ishlar olib borilyapti. O'sha litsey qimmatligi uchun, kamyobligi uchun uni hammasini o'rniga o'sha siz aytgan alternativ element sifatida uglerod va kremniy nanozarrachalari ishlatilishi ko'zda tutilyapti. Kelajak ularning orqasida.
Fizika fanining boshqa bo'limlari bo'yicha shunaqa ma'ruza qilib man plus o'zbek tilida ko'proq tushuncha bersangiz yaxshiroq bo'ladi.
Other people will give lecture in Uzbek, but if you want to hear me again about our own researches, I will come again, but I will speak in English or in Russian. It's to your choice.
Endi keyingi mavzularimiz ham ba'zi birlari o'zbekcha bo'ladi. Lekin sizlarga maslahat o'zi nima deydi? Ko'p tillik faqat inglizcha emas, ko'p tillikka o'rganish kerak. Rus tilida bo'ladimi, ingliz tilida bo'ladimi, nemis tilida bo'ladimi, o'zbek tilida bo'ladimi, qaysi tilda bo'lsa ham eshitishga, o'rganishga, shundan maksimum ma'lumot olishga harakat qilish kerak odam.
Qarang, sizga o'zbek savolim bor. Nima hisobiga neutron nurlari borda yoki uglerodda ko'proq yutilib qoladi? Hamma tushuntirib bor. Shuni do'stga chizib tushuntirib
Endi birinchidan men yadro fizikasidan emasman, ma'lumot yo'q. Yadro fizika sohasida emas. Lekin neutron nima uchun? Men prosta mantiqan javob berishim mumkin sizga. Nima uchun neutron ba'zi elementlarda ko'proq, ba'zilarda kamroq yutilishi mumkin? Qachon? Qayerda? Mana oddiy hayotdan olib qarang, har qanaqa narsani. Bironta narsada, masalan, suv nima uchun qaysi nonga ko'proq yutiladi? Quruq nongami yoki yangi nongami? Qurib qolgan, haligi suxari yo'q qolgan nonga tezroq yutiladimi? Xo'p, demak, neutron qanaqa elementga ko'proq yutilishi kerak? Qanaqa yadroga? Neytroni kam bo'lgan yadroga, protoni ko'p bo'lgan yadroga. Neytron ya proton va neytronlarning balansi bor yadroda, to'g'rimi? O'sha balans oshib ketsa, masalan, neytronlar soni oshib ketsa, bu yadroni radioaktivlikka olib keladi, parchalanishga olib keladi. Nima uchun katta transuran elementlar hammasi tez radioaktiv, hammasi yuqori radioaktiv va hokazo hokazo. Chunki o'zini og'irligini, hali semiz odamga o'xshab, o'zini og'irligini o'zi ko'tara olmaydi. Bo'linib ketishga harakat qiladi. Natijada haligi ortiqcha neytronlar, chunki qarang, masalan, uranni olsak 200 necha? 238, 235 nukleonlar soni. Protonlar soni 92 ta. Neutronlar soni ancha ko'p. Demak, o'sha neytronni chiqarib olishga harakat qiladi.
Uni ushlab qololmaydi deyapsiz, uning ichida protonlar bilan neutron bir-birini bog'lab
turishlar yaxshi bilasizlar, masalan, yadroda o'zi yadro kuchlari, yukava kuchlari bor, to'g'rimi? Yukava kuchlari o'sha
Ideki yukava.
Ideki yukava kuchlari bilasizlar, kuchli yadro o'zaro bog'lanishda o'sha proton va neutronlarning o'rtasidagi o'sha kimyozon almashinuvi deyiladi, virtual zarrachalar va hokazo, to'g'ri? Endi savolingiz nima edi?
Nima uchun neutronlar aynan
ko'proq yutiladi boshqa metallarga qaraganda.
Endi suvda tushunarli. Suvda vodorodga yutiladi, chunki vodorod protonga boy, unga sherik kerak, neutron kerak.
Xo'p, bosh miyada ham masalan suv tarkibida suv bo'ladi. Unda ham ko'p yutiladi unda.
Bosh miyaga?
Bosh miyani oladigan bo'lsak, tarkibida vodorod ko'p. Vodorodga bog'lasak bo'lmaydi endi.
Tarkibida suv. Siz aynan bosh miyani olyapsiz. Umuman organizmda suv ko'p. Suvsiz.
Yo'q, siz suvga bog'laganingizda yana vodorodga bog'layapsiz, yana shunga bog'layapman-da. Endi
suvga nima uchun suvga ko'p yetiladi deganiga javob sizga chunki vodorod ko'pligi uchun yetiladi. Chunki vodorodda bitta proton bo'lgani uchun neytronni yutib olishga imkoniyat bor. Xuddi shunaqa ahvol masalan borda ham. Borni atom massasi necha? Hozir tamam. Tak, tartib nomeri 3. Yo'q, 6. Tartib nomeri 6, atom massasi 12 adashmasam. 12. Demak, balansda turibdi. Protonlar bilan neytronlar soni, to'g'rimi? Demak, neytronlarni yutib olish ehtimolligi bor. Uning ustiga mana yana bitta narsaga, bir nechta faktorga qarash kerak-da. Yana bilasizlar, masalan, atom yadrolarning klaster modeli bor. Alfa zarrachalardan tuzilgan klaster modeli bor, yadrolar. Qanchalik alfa klasterlardan iborat bo'lsa yadro, shunchalik u mustahkamligi yuqori bo'lib boradi. Masalan, ko'pincha savol tushadi. Nima uchun yer shari aynan uglerod ko'p, nima uchun butun hamma joy yerlar, masalan, yerimiz kremniy ko'p, mana tuproq, yer hammasi kremniyning hisobiga, to'g'rimi? Asosan mana bu qolgan narsa, masalan, organik butun dunyo, insonlar, hayvonlar, daraxtlar va umuman uglerod ko'p nima uchun? Chunki bundoq o'ylab qarasangiz, hammasi klaster modelga olib keladi. O'sha ya'niki haligi yadroning ichidagi geli alfa klasterlarni haligi soni bilan olib keladi. Masalan, alfa klasterga proporsional bo'lmasa, uni demak unaqasi stabilligi kamroq bo'ladi. Masalan, milliard yil emas, 10 million yil va hokazo hokazo. O'shaning hisobiga masalan elementlar ham o'zi saralanib qoladi. O'shaning hisobiga biz sizlar bilan uglerod, kremniy, o'sha kislorodga o'xshagan elementlar ko'p bo'lgan zamonda yashaymiz. Agar salgina shu munosabat buzilgan bo'lganda edi, bizning dunyomiz butunlay boshqacha bo'ladi. Uglerod, kremniy emas, asosiy narsalar oltin, kumush va hokazolar bo'lishi mumkin. Bor, litiy va hokazolar bo'lishi mumkin.
Yana kimda nima savol bor? Savollar bormi? Takliflar? Unda bugungi mavzumuzni shu yerda to'xtatamiz. Albatta bildirib, bugungi mavzumizga kelganingizdan biz minnatdormiz. Keyingi mavzularimiz albatta men umid qilamanki, ko'proq auditoriyaga odam kelib eshitadi va qiziqish bildiradi. Va bitta narsaga amin bo'lishingiz kerak, biz ona tilimizni yaxshi ko'ramiz. O'zbek tilimiz ona tilimiz. Lekin sohamizni tili emas. Fizika, fani, fizika sohasini tili bu ingliz tili va rus tili hisoblanadi. Shuning uchun albatta kelajakda ilm yo'lini tanlaysizmi, siz majbur bo'lishingiz kerak bu tillarni o'rganishingizga va bu tillar bilan muloqot qilishingizga. Shuning uchun harakat qilishingiz kerak. Har kun aynan mana shu tillar bo'yicha hech bo'lmaganda fizik terminlarni boshidan o'rganib borsangiz, asta-sekinlik bilan qaysidir muhitga, auditoriyaga tushganingizdan keyin albatta gapirib keta olasiz. Bu o'zingizning sohangizdan boshlanishi kerak. Ya'ni fizik terminlarni bu tillardagi tarjimasi qanaqa bo'ladi? O'shanda ma'ruza yoki biror bir seminar nima haqida gap ketayotganligini siz tushunasiz. Bu gapirib ketish keyingi masala hisoblanadi. Tushundikmi? Rahmat sizlarga. Ustozga kattakon rahmat deymiz. Fakultetimiz nomidan mashg'ul.
Dear Professor, first of all, I would like to express my gratitude on behalf of all students here for the very interesting presentation. Particularly the obtaining method of nanoparticles were very interesting for me, and their applications in hydrogen production with intense radiation was very interesting. And the second one was as a member of for our modern batteries that sodium. You mentioned it was news for me, and thank you. And my question is, what's the obstacles for sodium to get to replace with the lithium batteries? Is there any obstacles to get that?
The obstacles is the same as for silicon solar battery, which are held by oligarchs. This is economic reason. They just do not want to give up the market. The same is with lithium. Even if the sodium is better, somehow is also is cheaper, the oligarch, the existing industry, they do not want to give some room for the competitors. It's not physical reason, it's economical reason.
All right. Thank you so much.
Rahmat sizlarga. Sog' bo'ling.